AP Stats. I hope you guys are having a good day. This is just a review video for chapter 11, which is all about the chi-squared test. So I'm going to try to do a quick overall review and then hopefully be able to go over at least one problem. All right, so overall, this entire chapter, there were 3 different tests. The first one is the chi-squared goodness of fit. Second was the chi-squared test for homogeneity. And last but not least was the chi-squared test for association or independence. All right, so the difference is the chi-squared goodness of fit is for a single population and a single categorical variable. So an example might be, is the distribution of M&Ms, of the color of M&Ms, truly what the company claims them to be? So your single population is regular M&Ms, your single variable is color, and then you just have the distribution of the colors that you're testing the claim for. The chi-squared test for homogeneity tests 2 separate populations but 1 variable. So, for example, it might be and it tests to see if the 2 populations are the same. So for example, is the distribution of colors of regular M&Ms the same as the distribution of colors of peanut M&Ms? And it can also be for more than 2 populations, obviously. And in fact, if you are only comparing 2 populations, you could also do a 2-sample z-test for the difference of proportions. So that's exciting. And the chi-squared test for association or independence is comparing 2 different variables and basically trying to test to see if there's an association or a relationship between 2 separate variables. So in the M&M case, the question is, does the type of M&M independent of the color distribution? So it would be essentially mathematically the same test as number 2 in this case, but it's just asking a different question. Basically, is there an actual relationship between these 2 variables? Common mistakes. All right, common mistakes we see on the AP. Number 1 is using the wrong test. Or using 2 tests at the same time. So always pick 1 test and go all the way with it. Make sure that you're looking at your data. Is it categorical or quantitative? Do you have 1 population or 2 populations? What is the question asking you? So make sure you spend a decent amount of time really thinking about, how do I answer this question with statistics? Number 2, make sure that your expected values and observed values are counts, not proportions. That is a very common error. Type of data. If the data is quantitative, you can't even do a chi-squared test with it. Ding. Number 4, rounding expected counts. That is bad. Do not round your expected counts. That means that you don't really understand what an expected count actually is. An expected count is what we'd expect in the long run after repeating this millions, like tons and tons and tons of times. So rounding them, just because you think they're supposed to be a whole number, means that you don't really actually understand what an expected count is. So don't round the expected counts. Concluding, never accept the null hypothesis. Never accept the null hypothesis. You are always rejecting or failing to reject. You either have enough evidence to say that I think the null hypothesis is wrong, or you have enough evidence to say I don't think I have enough evidence to tell whether or not the null hypothesis is wrong. When you're stating your hypotheses, make sure you're talking about the population and the parameters. You do not want to say anything about sample or statistic in the hypotheses. Remember, you already have your sample and your statistics. That's why you took the sample. You have it. You don't need to test it. Couple things when checking conditions. Number one, don't just write what the condition is and then just check it off. You have to actually show us the values. So for the expected counts, remember, checking conditions, a very common error is that people put the observed values, so what you got in your sample, in the checking conditions part, but that is not correct. You have to do the expected counts. And lastly, another common error is that people sometimes put the expected values in their calculator, but they don't actually write it down on the formula on their sheet. And this is a problem because we need to know, do you actually know what you're doing? Do you know how to calculate the expected counts? And we need to see that you've actually done it. So you really have to have every single expected count on your paper. All right, let's try some examples. This is a free response problem from 1999. But the cool thing is that it's about the Colorado Rocky Mountain Service, which is cool because we're here in Colorado. Okay, anyways, they want to study the behavior of lost hikers. If more were known about the direction in which lost hikers tend to walk, then more effective search strategies could be devised. 200 hikers selected at random from those applying for hiking permits are asked whether they would head uphill, downhill, or remain in the same place if they became lost while hiking. Each hiker in the sample was also classified according to whether he or she was an experienced or novice hiker. The resulting data are summarized in the table below. Okay. Do the data provide convincing evidence of an association, thinking, categorical data, association, hey look, there's a two-way table, maybe I need to do chi-squared test, I don't know, for association, between the level of hiking expertise and the direction the hiker would head if lost. Give appropriate statistical evidence to support your conclusion. All right, let's do it. Okay, because of that word association, you should be thinking chi-squared test for association or independence. Okay, so remember, number one, you have to state what you're going to do, at what significance level you're going to do it, and what your hypotheses are going to be. So we're going to be performing a chi-squared test for association to see if there's an association between hiking expertise and direction the hiker would head if lost at an alpha equals 0.05 level. We also have to include our hypotheses. A null hypothesis is always that there's no change, or there's no association, or no difference. So in this case, our null hypothesis is that there's no association between hiking expertise and direction. Then our alternative hypothesis is that there is an association between hiking expertise and direction. All right, planning, we need to check our conditions. So the first one is random, second one is independent, third one is large enough sample size. So let's do the first two first. Should be pretty easy. Okay, random. Yes, it says right here, 200 hikers are selected at random from those applying for permits. Independent? Yes, it is probably likely that there are more than 2,000 people applying for permits because our sample size was 200. We need the 10% rule because we're sampling without replacement. Third condition, is your sample large enough? So for this, you need to actually calculate all of your expected values. And so I'm going to actually go and do that in the table. And you can do that, just make sure you indicate what those numbers are. I just have to mention, my roommate is so weird. Earlier he was listening to classical music, and now he's listening to, what's it called? Let the bodies hit the floor. Let the bodies hit the floor. That one. Let the bodies hit the floor. It's quite a range of music. Anyways, okay, large enough sample. I like that song. It's a good song. All expected counts. Okay, greater than or equal to 5. Okay, first we gotta find all of our totals. So, I need to find our novice totals. So 50 plus 50 plus 20 is 120. So I'm going to write that in. And then my experience totals are 70, 80. My uphill totals are 30, downhill totals 80, and then remaining in the same place is 90. And just remember, for your expected values, you need to do your row total times your column total divided by the total total. Total total is 200. So for my novice, right, with this box, we need to do our row total, which is 120, times our column total, which is 30, divided by our total total, which is 200. So our first expected value is 18. Our next one, we could do downhill novice, in which case we need our row total, which is 120, times our column total, which is 80, divided by our total total, which is 200. And we end up with an expected count of 48. Same thing for the rest of them. I'm just going to fill them in. All right, so now that we've calculated them, we can say that in our plan step, number 3 has been checked off. So we would say something like, yes, all of them are greater than or equal to 5. C table, and then I just wrote C table for expected counts. Next, calculations. Okay, so we need first our chi-squared value. So let's write that formula in, which as a reminder is on your packet. Observed minus expected squared, all over expected, and then plug in at least 2 of the terms with a dot 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 in between, and then you can do the rest of your calculations in your calculator. All right, so it looks something like this. 20 minus 18 squared over 18 plus dot dot dot, 40 minus 36 squared over 36. And then we just plug all this into our calculator. Okay, so we're gonna have to plug all this into matrices. So we go to second matrix, and we want to edit one of our matrices. So let's make our observed values in matrix A, and now I have to go back up to my table, and I have a 2 by 3 matrix. Okay, so then I go 2 by 3, and then I want to enter all of that data. Those are all my observed counts. So then I need to do that again for my expected. So then I'm going to go to matrix. I'm going to edit matrix B, which is also 2 by 3. And then I'm just going to enter all of my expected values. All right, so then all we have to do is actually calculate our test statistic. So I'm going to go to stat tests, maybe, if it likes me. And then I'm going to go to not my goodness of fit test, because that one's just for a 1 by 1 table. Not a 1 by 1, but you know, only one row. So we go to the chi-squared test, and we have our observed in A, our expected in B, and then we want to calculate. And I have my chi-squared value, which is 1.5, my p-value is 0.47, and my degrees of freedom is 2. Alright, so I just entered my chi-squared value, which is 1.504. The p-value, remember, is the probability of getting your test statistic or anything more extreme. So I'm actually going to write out what that means. I'm going to say that that's the probability of my chi-squared value being larger than or equal to 1.504. Okay, so that is my actual p-value, and that equals 0.4713. And then my degrees of freedom, remember, is the number of rows minus 1 times the number of columns minus 1. So I'm going to write that in to show my work. And then I just need to conclude in context. And since my p-value is greater than my alpha level, I'm going to fail to reject the null hypothesis and say that I don't have enough evidence. I do not have enough evidence to say that there's an association between those two variables. All right, since our p-value is greater than alpha, we fail to reject the null hypothesis. We do not have sufficient evidence to say that there is an association between hiking expertise and which direction they'd go if lost.